Good afternoon, everyone, and welcome to today's webinar titled How to Read a Report in 2 Minutes or Less. My name is Kathy, and I am a Customer Engagement Specialist at TestOil. I will be your host today. Before we get started, there are a few things I want to go over. First, everyone is muted. We are recording today's presentation, and by being on mute, this will ensure a high-quality recording. Second, please feel free to use the question box in the GoToWebinar application. We would be happy to answer any questions that you have. Finally, the webinar recording will be distributed later today along with a survey. Look for that in the email you registered with. So let's get started. Today's webinar is presented by Evan Zabowski. Evan is a certified lubrication specialist and a senior technician advisor here at TestOil. If you're ready, Evan, I'm going to turn it over to you.
Great. Thank you, Kathy. So yes, today's webinar is about how to read a report in 2 minutes or less, but obviously it'll take me more than 2 minutes to show you how to do it. But the goal is how to get you efficient at reading reports so that you don't spend a lot of time getting through the report itself and spend more time trying to correct what the report is telling you is an issue. Now, the perception with oil analysis is that it is a hard task and that it is difficult to do in a short amount of time. But the reality is, it's not really that hard. It's just easy to make it harder than you need to. So my goal is to show you how to simplify getting through a report so that you get the information out quickly and efficiently, but not waste a lot of time chasing things that don't need to be looked at this moment in time. Now, the way that I've seen things happen over all the years of doing oil analysis is that there's some pretty common mistakes people make while they try to read a report. And probably the most common ones fall into about 3 groups. And the first group is those who try to interpret on the fly, meaning that as they read the report with each new piece of information they absorb, they immediately try to understand and justify what it's telling them. A common example would be to see a report and one of the first things on the report is high iron content. People start to then question, where is the iron coming from? And they start to wonder what it could be caused by, and they just start chasing iron. The point is, maybe iron isn't going to be the focus of this report. Maybe you'll read later about high water content or particle counts or something like that that is the true cause of the iron being there, and that's what you need to focus on. So basically, it's people just not waiting for the whole picture to appear before they start interpreting. They just, at the first sign of any data, make an interpretation, or at least attempt an interpretation. The second group of mistakes seems to fall into the category of people who are just trying to extrapolate from a little bit of information a bigger picture than is really there. And a good common example of this one is just to stay with this iron and particle count example. And when people see a high particle count, they immediately assume it's the cause of wear. But the question should be better asked, is the particle count causing any wear? Does the iron count go up in relation to the particle count? Perhaps the particle count itself may be the iron. I mean, these are better questions to ask. So you need to read, of course, the whole report to tie this all together and look at the correlations that don't exist and see what they tell you. So essentially, it's just not using all of the report to do the interpretation. And I know that these two, might sound a little similar to each other, but they're in fact completely different, and often are main problems that people have when they read reports. The last one, and this is not necessarily recognized as being a common issue because most people don't think it's an issue, but I'll show you why, is that a lot of people will ignore a report that comes back completely normal, or even if they have a report with some alarms on it, they ignore all the normal data. And that is also a bit of an issue. So again, we're not using all the data. But when we do this, what we're actually doing is we're just reacting to the alarm. So we're not making oil analysis as predictive as it should be. We're basically leaving it to be reactive. So the best way to illustrate these 3 issues, I thought, was to use some pictures rather than use oil analysis reports. So to illustrate the first one, I'm going to show you a rather shocking image. And I'm not going to show it for very long, just because it is a bit sensitive in nature. But let's just walk through this and you see what I mean. So here's the first picture. Now, you only had a couple seconds to look at that one. What emotion did that picture give you? Did you see the gun pointed at that man's head and think something bad's going to happen? Or do you think something good was coming out of that picture? There's some humanity there. You probably felt that first emotion. It probably was more something bad was about to happen. There's nothing really in that snippet of a picture that would say something good was going to happen. Now, let me show you the same image again, but cropped a little bit differently. Now, again, I only gave it to you for a couple of seconds, but what was your immediate reaction when you look at it? It probably was not one of dread. It was probably more of relief. It actually looks like this man's being helped and everything's okay. But here's the issue. Let me show you the whole picture. This is the entire picture, and as you now see it in its entirety, you can take, with the full context of the picture, that gun is not actually being pointed directly at the man's head. That was a conclusion we jumped to based on the short snippet of information we saw in the first image. But in fact, the humanity is there, as we correctly surmised in the second image. But seeing it as a whole, we truly understand what's going on in this image. And this is what I mean by about interpreting on the fly. If you read this image from left to right, the first thing you'd see on the left is a gun apparently pointed at somebody's head, and you would start to assume bad things. Only by the time you got to the right-hand side of the image would you realize that no, in fact, something good may be occurring here. But now let me give you another example using photos. And this is, again, to get to the second point about extrapolating a bit too ambitiously. So here's a photo of the famous actor Harrison Ford. And if you were to be wondering what emotion he's feeling, you'd probably think something along the lines of anger. If you were to try to create the entire image of what he looks like in your head right now, you'd probably come up with something like this. Right? And all I did was take the one half of the image and flip it to duplicate the other half of his face. But sure, he kind of looks angry in that picture. But now let's see another picture of Harrison Ford. In this picture of Harrison Ford, you probably think, well, he actually looks kind of happy. And again, if you're to try and extrapolate the full view of his face, what that picture might look like, you're going to get something like this. Now, it looks a bit odd. His neck seems a little too thick, but overall, yes, his appearance is kind of happy. The funny thing about both these examples is that it's actually the same image. You are probably now realizing that Harrison Ford has an asymmetrical face, and he's a man who can look both happy and angry at the same time. But that's just the issue that we have when we read oil analysis reports. If we only look at a part of the data and try and guess what the rest of the report is telling us, or just think that the rest of the report supports what we're seeing in one, we extrapolate in ways that don't represent, again, the true image, the full context of what is happening. Now, the last thing I said was a lot of people ignore normal reports and normal data. And the best image I could think to show you what that is like is this. Basically, if you only take the time to read a long report, it's pretty much the same as using a smoke detector to tell you when your muffins are done baking. And of course, we can all realize that's probably not a good idea. So I need to show you now how you're going to get through reading a report in that efficient manner so that you're doing all the things right and none of the things wrong that I've just described. Now, before I get to that, just a couple of preamble bits here. When it comes to interpreting a report, there's a few things you need to know to do a good interpretation. And essentially, I find they fall into two categories, basic and advanced. And a basic interpretation is typically what is done at the laboratory level. And to do a basic interpretation, there's essentially four things you need to know. One is you need to know information about the sampling procedure and location. Now, why this matters is on occasion you might pick up a report and say the particle count of the water content is particularly high, and it's completely out of the blue. There's been no history, no trend to suggest this is normal. Well, if you know your sample point is at a low point drain, or if you know somebody different has taken that sample than the usual person who takes those samples, you might surmise that the sample had a lot of debris or water settled near the sampling valve, and either they took it from that low point drain and did not flush it well, or they might have taken it from another location and again did not flush it well. But if you understand the sampling procedure and the sampling location, you can justify in your mind what some of these anomalies might be, and you would rather retest to confirm than simply react to them. Now, another thing that is very important to understand is limitations behind the testing. I spend a lot of time in our multi-day classes talking about this because a lot of people assume every test tells you everything. And the fact of the matter is some tests can only tell you so much, and some tests are significantly inhibited by the type of sample that you submit. One of the best examples I can quickly give you is the comparison between your wear metals and your particle counting. Now, most people will assume that if your particle count is high, you're going to have a lot of wear metals. And some people assume that if you have a lot of wear metals, you might see some of those show up in the particle count. But either way you look at it, people assume those two tests should correlate directly. If one is high, the other is high. But the truth of the matter is elemental spectroscopy measures particles primarily in the 0 to 5 micron range. Somewhere around 5 microns, the accuracy begins to take a nosedive, and by about 10 microns, it pretty much doesn't measure those particles accurately at all. So when you think about this 0 to 5 micron range, and then you compare that to what particle counting does, well, particle counting starts at 4 microns and up. So there's very little overlap in terms of the exact same particles that are being measured by both tests. So what that means is they don't necessarily always correlate. But funnily enough, if you're good at interpreting reports, you may know that the lack of interpretation can be just as telling. And what I mean by this is if you have a high wear metal count but a low particle count, it means all the particles are small and therefore probably caused by normal wear modes. If both tests are high, they correlate the way you might expect, it indicates you have both small and larger size particles, which means it's transitioning from normal to abnormal. But if your wear metal count is low and your particle count is high, it means you've got nothing but large particles. And that could mean of greater severity to the problem. The next thing we need to know is equipment metallurgy. Now, you either learn this the easy way or the hard way, because you will find that upon rebuilds or teardowns, you will start to learn what things are made out of what different metals. And different components sometimes contain metals we don't necessarily expect. As an example, if I was to find some high copper values in a gearbox, I would immediately be curious, where is the copper coming from? And this would be a very easy answer if I knew one of the gears was bronze and the other one was steel, because I would know that the copper was coming from the bronze gear. But if you look at a gearbox and you find out that both gears are in fact steel, both shafts are steel, and both shafts ride on steel bearings, you suddenly would be at a loss as to find where the copper was coming from. But when you get down into it, if you look at a rolling element bearing, frequently they employ cages, and the cage is not always made of the same material. It could be that the cage is made from brass or bronze, and now you have an answer as to where the copper is coming from. And that helps tell you how severe the problem may or may not be. So little things like this, you kind of learn through experience, or at least learn by asking a lot of questions. The last thing we need to do is employ trending. Trending above all else will catch the kind of problems that we're looking for on an oil analysis report. Relying on alarms is going to be misleading at times and not come early enough. But the point is, a basic interpretation needs knowledge in at least these 4 areas, and this is something that labs do well. But to get to that advanced interpretation, you need a little bit more. And what I'm suggesting that you need knowledge of to do an advanced interpretation is typically only the kind of knowledge that the end user of the oil analysis will have. First category is they need to know how the equipment is configured. Does this thing contain a secondary loop skid? Does it have an additional volume of oil to it? Is there filtration attached to this loop skid? Is there any other performance enhancing options to it? Cooling, varnish, water removal, things like this, because they can help explain why the data is doing what it's doing. Another factor is operating conditions. Is this thing being run at longer intervals? Well, it's hopefully fairly straightforward to think that the longer the oil is run, the more wear, contamination, and degradation you should see in that oil. So you may achieve higher and higher values than you've ever seen previously simply by going longer than you have. But if you don't tell the lab this, How will they know? And they start alarming your reports based on past history. But other factors like, is it hotter? Is it more humid? Are you running it faster or under greater loads? Are you running it intermittently? If there's any change to the operating conditions, they will have direct correlation to some of the data on your oil analysis report. And the last category is any maintenance activity. If you've topped up some of the fluid or changed out some of the fluid, if you've applied any sort of secondary filtration, or you call it kidney looping or side stream filtration, all of these, of course, can take away some of the data that we're seeing on the oil analysis report and can explain some of the variances that we're seeing. So to do a really advanced interpretation, I'm suggesting these are the kinds of things that one must bring to the table, and the best person to do that is the actual end user. So with the end user in mind, these are the steps that it will take to read through an oil analysis report in 2 minutes or less. So the steps are quite simple. They really shrink down to about 3 key things, and the first one seems so simple. Read the whole report. That's it. Now, when I say read the whole report, what I'm also putting in there is be methodical about this. By reading the whole report, you should basically start at the top and continue all the way to the bottom and read every piece of data. And I mean every piece of data all along the way. Don't skip around. Don't eventually get to it. Just be methodical. And as an example, I've had customers who, with a hard copy report, will place it on their desk and then put a ruler on top of that piece of paper. And they will slowly slide the ruler down the page to ensure they don't jump ahead and read anything without having seen what was there before. Not everybody needs to go this far, but okay, whatever works, but read. And by following my next couple of steps, I'll show you how you can get through that whole report in 2 minutes or less and still get all the information out. Now, as you're reading the whole report, there's really one task that you're trying to do, and all you're trying to do is identify abnormal values. And by an abnormal value, this may be something that was alarmed by the lab. This may be something that appears out of trend. This may be data that has never done what it's done before, and gone in a different direction, hit a certain level that's never been there, whatever it may be. But all you're saying is to yourself is that data doesn't look right. And it doesn't matter how sensitively you judge this. If you don't think it looks right, then that's fine. But what I want you to do as you read every piece of data on the report and you find something that's abnormal, categorize it. And the categories are simple. It's either a cause or it's an effect. Now, as you assign it a cause or effect title, 2 things. One is don't try and figure out what it's a cause of, what it's causing, is it an effect of this or an effect of that. Just assign it cause or effect. That's it. Don't go any further. But also, you're allowed to change your answer. If you start reading the report and you find something, you say, I think that's a cause. But you keep reading the report and you find something later that you go, I think this is a cause, and I kind of think it caused that other thing. Go ahead and change the first cause to an effect. At the end of doing this action, you should then have grouped all your answers into cause or effect. And no matter how many things are alarmed on the report and how many things you find abnormal, I assure you, almost every report you will identify however many causes you came up with into 1 or 2 groups. That's it. So if you have a whole bunch of things and you think, well, this is a cause, this is a cause, this is a cause. If you ultimately think about it, you go, well, those 3 would happen together. So that is still just one cause, one overall overriding parent cause to the group. So once you've identified this 1 or 2 categories of causes, now you need to do the next step, and that is basically decide what to do next. Think of it as I'm writing up a work order to give to somebody else. What do I ask? Now, the little tidbit I put here at the bottom is I'll assure you that recommending an oil change is seldom the correct answer. It's a very common answer, I'll admit, but a lot of people who do this are not doing it correctly. Right? Suggesting that changing the oil fixes the problem does one thing really well. It makes the next report look good. But you didn't fix anything. You just erased the evidence that said something bad was happening. So the problem will likely return, depending on what it is. But more times than not, changing the oil doesn't actually fix the true issue. So let's try 2 examples here, following my pattern, if you will, of what to do. So I've split the first example across 3 slides, just so it's as readable as possible to those of you watching on screen. And I'll use this laser pointer here so you can follow along with what I'm looking at. Now, when I say read the whole report, I do mean the whole report. We start up here in the top left. So you read, what is this? It's an anti-friction bearing. It's got an AW46 oil in it. Now, I can pause right there and say AW46. There's 2 things I know about this oil before I even read the report now. AW means it's an anti-wear oil. So I know right away it's got a phosphorus and zinc additive chemistry. Likely it probably has some calcium or magnesium in it too, but I know for a fact it has to have phosphorus and zinc in it. Secondly, it says it's a 46. I now know that the viscosity should be 46 centistokes at 40 degrees Celsius. So I know this before I've even read the report, but I have an expectation of what I'm going to find. Now, in this particular example, sump size is not identified to us, and a lot of people ask, why do we need sump size? Well, sump size has no bearing on the actual numbers that we report to you, but it does have a bearing on the recommendation you can put forth. If you tell me this sample was taken out of a 5-gallon system to lubricate a bearing, versus you tell me it's out of a 500-gallon system to lubricate a bearing, I would change my recommendation. Right? If we find that there's something wrong with the fluid, it's contaminated with particulate or water or another fluid, and there's only 5 gallons of it, we'll just tell you to change it. But if you tell me there's 500 gallons of oil and there's some contamination to it, we might recommend that you filter it, because it's worth saving 500 gallons of oil. But anyways, we keep reading across the report. So you confirm the sample information, you can see the date, make sure you know which machine it's coming from, these kinds of things. Confirm it's even you. I know it seems a bit silly to justify your own plant name, company name, and this, but some of our customers have multiple sites, and one of the first things you should do is make sure this is your report. Because if it's not your report, well, you're already done then. You can just pass it off to whoever needs to read it. But all kidding aside, we read the entire heading. Doesn't take long, takes maybe a second to justify that the information in these 2 sections is actually complete. But having read this, I'm familiarizing myself with what I expect to find, what kind of machine it is, and I'm getting a clear image. Now, down in this section, you see problems identified by the lab. So this particular example I'm showing you says it has a high water content, excessive wear, and particle count. Now, the comments over to the right here are going to be related to those problems. So you've got some laboratory recommendations as to what's going on and perhaps what to do. Now, when you read this, this is, again, a basic interpretation done at the laboratory level. So you can agree with it, you can disagree with it. But what I ultimately want us to do is, as we read the report, come to our own conclusion, even if it doesn't match up with what the lab says. Because as the end user, like I said, you're privy to more information, and you might be able to account for some of the data in ways that the lab couldn't. But as we continue down the report, we're now going to get to the data section here. So let me explain just 2 things before we get into the numbers here, in case anyone's not familiar with the format. This first column here, the one marked new oil that's kind of shaded gray, this is what a virgin sample of brand new oil looks like as submitted by a customer. We do not get this data from the oil suppliers themselves, only through people who submit us a sample of the product brand new. So if there's ever any question about is it up to date, is it accurate, does it represent my oil, well, then you should probably send in your own sample and make sure we update it, and therefore it will be correct. But the next column to the right, this one here, this first column is not shaded gray. This is the most current sample, and this is the one, of course, we're focusing on when we read the report. But every column to the right is an older sample. So essentially, when you read reports, you're kind of trending them from right to left to see what's happening. Now, when I say read the whole report, again, I'm going to read this section, because in this section, what's one thing I noticed? Look down here at these bottom 2 rows, the lube hours and the machine hours. On this first sample, about 0. So that was a brand new machine on this sample. So this is essentially a baseline sample. The next sample, and then we continue the trend, you can see the oil's never been changed, because the oil has just as many hours on it as the machine does. So again, this is the kind of information you can gather when you read the whole report. So what's my overall expectation? Well, if the oil's never been changed, I do expect the values of wear, contamination, and degradation to continue to get higher and higher and higher. That is a trend I expect to see. The question is the trend following a normal path, or is it looking like it's abnormal? So now let's get into the actual oil analysis data. First number on the report I probably do not like is this iron value right here, because again, look at the trend. It went from below detection limits to 5, 25, 85. That's quite a step change right here. So if I say, okay, there's my first abnormal value, again, all I'm asking you to do is identify, is it a cause or an effect? And wear metals are caused by something else. Something is making it wear, a misalignment, a lack of lubrication, a contaminant, a particle, something. And I'm not here to decide what that is right now. Like I said, that's where we start interpreting on the fly. So all we do is say cause or effect. Well, it's a wear metal. It's an effect. The next number that looks abnormal is this lead value. Again, look at the trend. Very, very low, 9, jumps up to 49. That's an abnormal number. So I say I don't like this lead value. Well, is it a cause or an effect? Again, it's a wear metal. It's an effect. Now we keep reading down the report, and probably the next number that stands out as being a bit odd is this calcium value. Now calcium is an additive, and if we look at the additive value, we see the new oil has a substantially higher value than this current sample. However, again, by reading the whole report, we see that this baseline sample at hour 0 had about 40 parts per million. So as we move along here, really there's been very little change to this number. So I can't consider it abnormal because it really hasn't changed. Now, it doesn't compare very well here to the new oil value, but again, that may mean the new oil doesn't necessarily represent what this oil looks like. Even though this is brand new fluid in a brand new machine, perhaps there's residual contamination of preservation oil or any number of other factors that may affect this. But long story short, I don't have to say this is abnormal simply because it doesn't compare to the new oil. Again, I look at the whole trend here and go, no, it's fine, it's level. The same thing can be said with my phosphorus and zinc values. You might notice that they don't seem that close to these new oil values, but again, if you look at the trend starting here on the right and carry it all the way to the left, that trend is flat. So if I flip to the next page of the report, we've so far identified iron and lead as effects, and no other data so far has appeared abnormal to us. But as we keep reading the report, we do see some data for silicon, and the trend for silicon has been flat, and then there's been a sharp increase. Now, whether you believe 7 parts per million is an abnormal increase or not, that's up to you. If you think it's abnormal, I will simply ask you that question of, do you think it's a cause or an effect? And the easiest way to do this is to simply ask yourself, did silicon cause the iron and lead to go up, or did the iron and lead increasing make the silicon appear? And it's fairly easy to say iron and lead cannot make silicon appear, but if it was in the form of dust or dirt, could, of course, make the iron and lead appear. So silicon seems like something you would call a cause. Now, if you keep reading the report and you get down into the FTIR data, you will see the numbers compare very well with the new oil values here, and they trend from history all the way through quite smoothly. Once you get to this value, though, the other fluid, which is not a direct measurement of how much other fluid is present in the sample, it's rather a parameter that helps us identify if there's another fluid. And every oil's got its own unique baseline value. So the difference that I'm seeing here would, at first glance, suggest there's a contaminant in this product, 2 different fluids mixed together. But again, reading the whole report, I look at the history and go, no, the baseline value in this was brand new oil is pretty much the same as where we are right now. So again, I don't think there's anything abnormal in that data. I just have a second reason to question this new oil column and think maybe it's not entirely up to date for my current oil. Now, once I get down into the particle counting should stand out as abnormal. And again, is it a cause or is it an effect? Well, this is a difficult question to answer, because is the particle count high because it's containing wear metals? Or are the wear metals high because of all the particulate? So being that that's kind of a difficult question to answer, here's where I say, yeah, we're not going to extrapolate unnecessarily. Let's just keep reading the report and know that we have to come back to this particle count and assign it a cause or an effect. So the next piece of data is viscosity, and that has a nice flat trend. The acid number has a nice steady trend, but the water content has an exponential trend. This is not normal. So water as an abnormal value, is it a cause or an effect? Could the iron and lead present make the water appear? Could the silicon present make the water appear? No. So the water could be the cause of, as an example, the rare metals or something else. So we will call water a cause. So just to review real quick, the iron and lead we identified as effects. The silicon, if we believe it's abnormal, we would say it's a cause. The water is definitely a cause. And the particle counting we're going to have to come back to. But the last page of the report contains the analytical ferrography. And just to give you a 10-second how to read ferrography thing, the simple solution is this. Look at the first two categories and consider these two are the only ones that could ever be considered normal. You expect rubbing and rolling contact. So as long as the particles are small, these can be considered normal, regardless of the level that may be there. But when the particles are larger, and by small I mean around 5 microns, so when the particles are larger like this, regardless of level, they're abnormal. The rest of the categories, regardless of level, regardless of particle size, are always abnormal. So that's it simply put. Now let's interpret it. This rubbing wear says it's got a heavy level and they're larger particles. So this is abnormal. But rubbing wear is a form of wear. What's making it do this rubbing wear is something else. So we have to classify this as an effect. The sliding wear is definitely not normal, and these particles are large enough you can almost read the serial number off them. So we have to consider these to be very abnormal. But again, it's a wear factor. Something's making it wear. Something else is causing this. So it's just an effect. Corrosion. Well, it doesn't take much of a leap of judgment to think that the water content may have something to do with this, but we're not here to judge that right now. We're just deciding if it's a cause or effect. So yes, probably something like water would have caused this. It is an effect. Now, dark metallic oxides are the kind of particles you find from welding. And by welding, I mean when two surfaces come under such great pressure, they temporarily weld to each other, meaning that there was too little of a lubricating film in between moving surfaces. So something caused that to happen. So again, this is an effect. Red oxides is a fancy way of saying rust. Again, rust is usually caused by oxygen and water contamination. So again, this is an effect. So everything on this report so far, these are all effects. But when we get to this last category of dust and dirt, well, now you have something that probably is a cause. And if you think about this, what did we say was, what else did we say in the report was a cause? We said silicon, we said water, and we're undecided on particle count. Well, now that you've seen the whole report and can take into context, you can probably group the silicon, the dust dirt that you're looking at right here, and the particle count together and say all three of those have something to do with particulate contamination. The only other cause that we have left is that water. So we now have to decide, going back to the first page here, we have to decide what to do next. So having read through the entire report and just saying causes or effects, we know what the two causes are, particulate and water. Now, returning to the first page was just to remind us, this is an anti-friction bearing. So what is a likely cause for high particulate and water content? Well, an easy answer, and this is not dependent on it being an anti-friction bearing, it could be a lot of other kinds of machines. The simple answer is this: it's being ingressed through some opening. Now that opening could be a fill cap, a dipstick, a inspection cover, a breather, any number of openings in the system. So hypothetically speaking, let's pretend that we do tell somebody to inspect for sources of ingression. Look for ways particulate and water could have gotten in. So hypothetically speaking, imagine I tell you that the problem was so obvious it could be spotted from 20 feet away from the machine. Right? The dipstick was laying on the ground, or the fill cap was missing, or the breather was damaged or missing. Something's really, really obvious. So of course, the corrective action would be to fix or replace that. You put the dipstick back in, you tighten the cap on, you replace the breather, whatever it happens to be. Here's my next question now in this hypothetical situation. If you spot something that was obvious and you correct it, what do you do after that? Well, there's kind of two schools of thought. Some people think you should resample the machine, and some people think you should change the oil. So let me address both options. Suppose we simply resample the machine to see if we fixed it. The better question would be, when do you resample it? And the answer is, you do not resample it today, and you certainly don't resample it tomorrow. What you do is you wait for the normally scheduled interval to come back. Because if you sample it too soon after doing something, you're not likely to see much change. But then the next question is, if you wait that normal interval and you sample it under normal conditions, everything's just the way it's always been, what do you expect the next result to look like? And the answer is, if you fixed it, if that truly corrected the issue, the next result should look about the same. It won't look better unless there's significant filtration on the system that might help remove some of the particulate that's in gas. But what is there is there. The wear that has happened is not going to go away. The particulate that is in gas is not going to go away. The water that got in is not likely to exit much. So you're going to get very similar results, not lower results. Right? Some people think it'll get a lot better if you fix the problem. Well, no, because all you did was stop the problem. You didn't reverse the problem. Now, the other scenario, though, I said to you was some people suggest you change the oil. And as I said at the beginning of the presentation, changing the oil is not always a good solution. So what happens if we change the oil? Well, I guarantee you, if you wait for the next sample to come around, it'll look great because it's probably pretty new oil. So my other question I would ask you is, if you change the oil, how many samples will it take you before you figure out if you really did fix the problem? Because you can't count on the first sample confirming that, because it will always look better because it's much newer oil. The answer is, if it took us 4 samples to spot this trend, it probably could take us another 4 samples to see if that trend returns, because we cannot prematurely judge if the trend is returning on the first sample or two. You probably have to wait for that 3rd or 4th sample to confirm that. So the best answer would be, let's leave the oil in service, make a correction, sample it normally, and expect the results to stabilize. Now, given that that's the answer, a lot of people would then challenge me and say, yes, but I don't want to leave this bad oil in there. Look at the iron count, look at the water count, look at the particle count, and just say, I can't leave this oil in service. If I leave it in, it's just going to get worse. And you know what? I agree with you. But here's where I can make my point really strongly. At the very beginning, I said, of the 3 steps you have to do a good interpretation, I said, read the whole report. But one of the things that we're adding to this is that we read every report. If we can read the whole report and get it done in 2 minutes or less, we now have the time to read every report. And out of the 3 most common mistakes I said is people ignore reports that come back normal. So here's my next question, and this is why I returned us to the first page of the report. If you call this sample number 1, sample number 2, sample number 3, and the current sample, sample number 4, if you had taken the time to read every report that crossed your desk, and you had read each one of those reports as they came in, which report would you actually have caught this problem on? And if you look at the iron values going from less than detection, 5 to 25, lead going from less than detection limits, twice in a row, jumping to 9, this 3rd sample here appears to be the one that could have identified the trend. And if we go to the 2nd page and you look at water content in particular, it went from 90 parts per million to 400 parts per million, 3,000. That is not a normal trend. So you have a few pieces of data that definitely support the trend was there on that 3rd sample. You're not going to spot it as easily with silicon. Certainly the particle count did take a jump, but it's not necessarily that substantial. But this is why we take the time to read every report, and this is why I said earlier, a lot of people just use the alarms. And if you use the alarms, it's like waiting for the smoke detector to go off. And we could have caught it on this sample had we read every report. But no, if we wait for the alarms to go off, yeah, the oil's now too far gone to really want to leave in service. But if we caught it on this 3rd sample, we could have made the correction. We could have waited 1 more sample to confirm we did, in fact, fix it properly. And we would have caused a lot less damage to the machine. So this is why I say read every report, and read every report top to bottom, including its history. It doesn't take long to scan the report and see what values are abnormal, and it's a fairly simple process to identify, is it a cause or is it an effect? So let me give you another quick example here. Now in this one, I did remove all of the alarms from the lab. So there is no color on this report purposely so that we focus on reading the whole report. So again, starting at the top, we see it's a plain bearing. It's got a 5-gallon sump, uses an RNO 68 fluid. Well, RNO immediately tells me that this is an oil that does not have visible additives in the elemental spectroscopy results, meaning I do not expect any calcium, magnesium, phosphorus, zinc, any of those typically in the oil. It's a 68. It should have a viscosity of approximately 68 centistoks at 40 degrees Celsius. You keep reading the rest of this, you confirm the information, you can see the lab commented there was high wear and particle counts, and it has its comments related to those two. But now let's dive into the actual data. First thing we probably notice is that reporting on hours for the machine and the lubricant are all over the place and don't even seem to make sense. So we cannot trust the information that's here. Right? We didn't suddenly lose 34,000 hours on here unless we happen to replace or rebuild this. But we've got unreported data on either side. So this is really not trustworthy. There's nothing we can sort of ascertain from this data. Let's go down into the numbers. Should jump out right away, iron is exceedingly high compared to history. It's abnormal. But as I said before, wear metal, something's making that happen. Wear metal, it's an effect. Copper, it's an effect. Lead, it's an effect. Tin, it's an effect. And see, this is how we get through the report a little bit faster, because we don't have to worry about where all this metal's coming from. We need to figure out why it's happening first. But the next number after all these wear metal effects that we find is this calcium value. We've got a history of very low calcium, and it suddenly ramps up, and the new oil suggests there is none. And like I said up here, RNO already told me that. So I've got high calcium appearing in this sample. That suggests to me there's another fluid getting in here, because that would be a pretty common reason to have calcium show up. You know, it's typically an additive element, and if I don't expect this additive, well, then I've contaminated it with another product that does have this additive. So I'm thinking this is probably a cause, right? Wrong lubricant? Certainly could explain why I have wear. But carrying on, I look at phosphorus next and again decide this is abnormal. It's far above typical trend values and what the new oil value expects. So I say it's abnormal. Is it a cause or effect? Well, again, it's probably indicative of another fluid getting in there. So yes, it's a cause as well. Now we go to the second page of the report and we see a pretty stable trend on silicon. We see a pretty stable trend on most of the infrared results. Funnily enough, we actually see a very distinct rising trend on the other fluid value, but it happens to match new oil towards the end. So oddly enough, this actually suggests that earlier in history we had the wrong fluid there, and we've slowly transitioned it over to being the right fluid. So it kind of contradicts some of the other data, but let's keep reading and see what we have to say about this. The particle count is substantially higher than previous. When it's all 9s like this, it means it has maxed out the machine. So this is the highest particle count we can report. So is this particle count really high, causing the wear metals to be there? Or is this particle count the wear metals themselves? Well, again, we can't necessarily decide that easily, so why don't we just wait on that determination? Now we look at the viscosities and we see they're approximately 68. Which is what I had said at the beginning should be the viscosity. So when we identified calcium and phosphorus along the way as causes, I was suggesting it's kind of behind the scenes that one of the most common reasons for additive elements to change is that another fluid got in here. So what's curious is if that's the reason, if another fluid is really what's happened here, it's another fluid that did not affect the viscosity. So either it's the same viscosity or it's something that doesn't have an effect on viscosity. So that narrows down our list of suspects as we continue forward, but let's keep interpreting the report. Acid numbers a flat trend, there's been no water to speak of, so we go to the last page of the report, and again, simply put, the first two are considered normal as long as the particle size is around 5 microns. Any of these last ones are always considered abnormal, regardless of level, regardless of particle size. So when I look at this first one, I see a high level, but also it's large particles. So this is abnormal, but being aware, it's an effect. Sliding wear is high and very large, but still being aware, it's an effect. Dust and dirt, however, are high. So dust and dirt is a cause. So returning to the previous pages here, again, going to the first part of the report, I've identified a bunch of wear metals as effects, calcium and phosphorus as causes. The only other thing I really saw in the report was the particle count and the dust and dirt. So I can probably put the particle count and the dust and dirt together as one cause, and the calcium and phosphorus together as a different cause. So I now have to come up with an explanation as to what to do next that addresses both of those issues. High amounts of contamination, but also suggesting some of the contamination is a different fluid. So why I returned us to the first page was just to remind us this is a plain bearing with 5 gallons of oil in it. Given that it's a plain bearing, I'm going to make a big assumption here, but maybe you'll see where I'm going with this. I'm going to assume that bearing has a seal on it. And I'm also going to assume that that seal is independently greased. And if you think about that as a pretty logical setup for a plain bearing, it's not that uncommon. You now have a good solution as to where could you get another fluid and high levels of particulate contamination. Because if that seal is greased and it has been over-greased, and grease has migrated from the seal into the oil system, I can explain why do I have calcium and phosphorus. It could be a calcium thickened EP type grease. It could be that there's just calcium and phosphorus as additives, whatever the explanation is. But a little bit of dissolved grease would introduce the calcium and phosphorus and would not have an effect on the viscosity. So that's how I can justify why the viscosity didn't change, because the only other option that makes sense is that we've topped up or replaced this oil with an oil that is also a 68, but does not contain an RNO additive package and probably has something more like an EP additive package, which would also be heavily on the phosphorus side and potentially some calcium. So that could be possible. If you told me that you had both an RNO 68 and an EP 68 on hand in your lube room, we might consider that somebody just grabbed the wrong one and grabbed the EP instead of the RNO. Now that would explain either solution, the grease ingression or the wrong oil, could explain why we have so much wear particulate. But the wrong oil, being that we just put EP 68 in there, doesn't explain why the particle count went up and the dust and dirt up here, not at least entirely. So that's why I returned to the seal solution and say, yeah, well, if you over-grease the seal, you would have failed the seal. If the seal failed, well, then contaminant could get in. So that's why I lean to something like that. But that's the basic procedure that you follow in terms of reading these reports. Get through it quickly, identify the causes. Don't worry about the effects. They will sort themselves out if you truly think of something to address the causes. But like I said, stop interpreting on the fly, stop jumping to conclusions and extrapolate more solutions or problems from a little bit of data, and don't ignore all the normal data. Read the whole report, always. So in summary, what you want to do to simplify the way that you now interpret the report is follow these basic 3 steps, and in doing so, you're going to identify that true root cause and therefore come up with a more effective solution at preventing it from returning. You're now going to, of course, restore oil analysis to being a predictive technology rather than a reactive technology. If you can get through your reports more efficiently, you've now got the time to read every report, given the normal ones. And if you've done a better job with your interpretation and have now actually instituted corrections that make the problems go away or reduce the severity of the failures or issues, you're going to upgrade the effectiveness of your program and, of course, your reputation. Like those of us who've been involved in oil analysis for some time always know that it really, really hurts us if a machine fails under our watch. Because when the machine fails under our watch, people start to question whether or not what we're doing is effective. And that's always a difficult argument to try and win over when the data's staring you in the face that, no, we didn't catch it. Because then they go, well, then there's no point doing it. If it doesn't help, we're going to stop it. So what you want to do is show that it helps. And when you show that it helps, the other thing you do, and this is what everybody likes to see, is you increase your return on investment. You show that the oil analysis program is worth something, your time and expertise is worth something, and everybody wins, everybody's happy. So with that, I'll thank you for attending this webinar and taking the time to listen. If you do have any questions, please use the question or chat portion of your toolbar. And at this point, I'll turn it back over to Kathy and see if we've gotten any questions that have come in.
Okay, Evan, thank you. There are a couple questions. The first question I have, are there sample reports that I can print out to show a client how the analysis works?
Yes, we have examples of every one of our main styles of reports on our website. If you simply visit the website and go to the Services tab to see routine oil analysis, EHC, turbine, etc., click any one of those, and on each one of those pages there's a link to an example report that you can print and see what a full report looks like.
Okay, and then I have another question asking if my alarm limits can be changed.
Certainly. Give us a call and you will talk to somebody like Kathy, and she'll be more than happy to help you adjust your alarm limits if you feel that they're alarming either too sensitively or not soon enough. We're more than happy to customize people's alarm limits, for sure.
Okay, thank you so much. It looks like there's a few more questions, but I think it would be best answered through the email. I would like to thank everyone for joining us today, and thank you so very much, Evan, for presenting.
Yes, thank you.